So our second speaker is Alex Kontorovich from Rutgers and I guess AWS. Is that Amazon?
Yeah.
Okay. A case for formalization in research mathematics.
Okay, so thanks very much for the invitation. It's great. It's always great to be back in my alma mater. So thanks, Henry, for setting up the talk. I'm going to try to see if I can explain what these things look like from my point of view, having played with these tools for some time. So, you can imagine, of course, they were not contemporaries, but you can imagine Euler looking forward 100 years to Weierstrass and saying, I did all this calculus, and now you're saying it wasn't valid because it didn't use epsilons and deltas. Why do you need all of this formalization of calculus? You can imagine Kummer saying, we have this perfectly good notion of ideal numbers. Why all this abstraction when he's speaking to Other and the notion that ideals are the ideals as ideals of abstract rings are sort of the right way to understand some of the things that Kummer was doing. And I would say what's happening today with formalization is really not so different. Mathematicians throughout time have continued to refactor our epistemology, what we consider a rigorous proof. And as we just heard from Michael, there are many mathematicians who don't think this is necessary. And I think in a few generations, maybe not even that long, this will just be a part of normal mathematical workflow in the same way that we used to handwrite all of our manuscripts and give them to people who would typeset them for us, and now we just all use tech. And tech is just easier and faster, so we use it. And in the same way, Lean, which at the moment is clunky and time-consuming, it's already becoming, thanks to auto-formalization, usable in real time for research mathematicians, and the more those tools will come online, the more people will just use them, and this will be a normal part of our workflow. So, what's wrong with continuing to write mathematics in natural language? I don't think there's anything wrong. I think what we're doing is perfectly fine. But as a community through millennia, we continually discover new ways to understand our subject, to organize our subject, communicate it amongst ourselves and to the others. And I don't think formalization is, from that viewpoint, any different. So let me just say how I got into this stuff. Back up to 2019 when I first heard of Lean, and if I had a paper with some, slightly tedious, yes, I can do this calculation by hand, and I do a calculation like this by hand first to understand it, but you do this 3 times, you get 3 different answers. You just go to a computer algebra system, you put it in once, it says, yes, this is right, great. I don't have to waste time checking and rechecking this lemma as I write up my paper. Whereas if I have a calculation and a theorem, and there's lots of parameters, there's a q and a q naught and a c and a y and a theta and all of these, and I'm not writing in my head, they are all playing a role, but we don't write down every last detail in our theorems like this. And so it's so easy in lemmas to make a stupid little mistake. You drop a minus sign, the entire theorem, the entire paper is completely gone. And so this is not something that's that only exists in analytic number theory. There are a lot of areas in mathematics where a minus sign can ruin things. And so I'm just wasting time rechecking lemmas, hunting for potential minus signs. Couldn't there be a computer algebra system like a tool that would speed up my workflow? And so the obvious answer is to use something like Lean, an interactive theorem prover. If I could just formalize results as I go, then I'm not wasting time rechecking lemmas in the same way I don't any longer waste time rechecking algebra once I do it once. Okay, and of course the reality is no, as we saw in Henry's great presentation. This is an example from a course I taught last semester. I taught an undergraduate intro to real analysis course, and I taught it formally. And so this is the proof that if you have a subset of a closed subset of a compact set is itself compact. Okay, and you have to actually do something. Of course, in the prime example, you also have to do something, but what you have to do is much smaller. Here, you have to come up with an open cover and then show that cover then has a subcover. Where are you supposed to get that from? And so, I'm not going to go through this code line by line, but it basically is a one-to-one mapping of what you would do in natural language, but now written out formally. But you see, it's very, you have to know the syntax, it's time consuming. There are all kinds of things that you have to prove formally that in natural language you just sweep all of these details under the rug because your brain does it automatically. So, at least not by hand. So formalization doesn't speed up your workflow if you do it by hand. So as I started saying before, and as Henry mentioned, auto-formalization, tools that can do these things automatically are coming online. The most recent one, I just grabbed one off of, hot off the press. This is from, days ago. A group at Meta was discussing a tool which is open source, which it's open source to the extent that you have API to Claude or something, to your favorite frontier LLM, and it will auto-formalize textbooks. And this is some algebraic combinatorics book, and they show you side by side what the natural language is together with what the Lean statement is. So you can really read this. I mean, even if you have no experience with Lean, if we have Q is some finite set, P is a subset of it, and we're going to sum over all in between sets, -1 to the I, and we get some identities, some Mobius inversion on the level of sets. And here we have some, I didn't say what they're sets of, so they're sets of some arbitrary type. P and Q are finite subsets. P is a subset of Q. We're going to sum over the power set of Q of all of the, together with the condition that P is contained in I, -1 to the cardinality. Anyway, it just, you spend 5 minutes learning how to parse these things, and you can understand the formal statement. You can understand the formal statement corresponds to what you think the informal statement is, and off you go using formalized tools. Okay, so with today's tools, really today's, I mean, I couldn't, a month ago I wouldn't have said that. Okay, things are really rapidly accelerating to the point where with modern tools, and if the subject that you're working on has been sufficiently developed in MathLib. If you're doing PDEs, I'm sorry, there's still more work that the foundations the definitions have to be brought into the library. This mono repo, this big repository that has done the hard work of preparing you for auto-formalization. Then, at least in principle, you can get AI to help you formalize whatever it is that you're interested in. So, please.
It formalizes based on an existing source.
You have to tell it what you want it to formalize.
You tell it the result, or you tell it the result and the natural language proof?
So, oftentimes these days, when you tell it the result, it'll be happy to write out informal proof for you. So they can do it in one fell swoop. Now, where they're reading that result, they've read the entire archive, they've read all kinds of things, copyrighted things, and they'll write out a proof for you. They won't tell you where it comes from. But the problem of getting it to write out an informal proof and formalizing it, or having humans write out an informal proof and having it just do the translation, I don't see those as different problems anymore, because the LLM can give you what it thinks is an informal proof, and then it can do the translation too. Yes, those are slightly separate components of the workflow, but AI these days can do both. So, okay, so whether it's humans that are doing the formalizing or AI that's doing the formalizing, once you've digitized mathematics, it unlocks all kinds of new possibilities in what you could do with mathematics. So, as we heard, this is another hot off the press from a few days ago. This is a project, I mean, I've been following these guys for a few years now. They wanted to keep everything very hush-hush, and they just announced their existence to the world. This is the so-called LANA, Lean for Anabelian Geometry project, which there's a second project trying to formalize Mochizuki's work as well. They're going to have an announcement in July. Basically, they've formalized, in some sense, everything up to this proposition 11, whatever it is, and they've pinpointed the place where they can no longer convert to mathematical statement what's written in Mochizuki. And so they've sort of posed the challenge to him and his team. In July, we'll say this is the gap. This is the point where we don't understand what's supposed to happen. So it is the same location as the Schulze-Dix, but it's a different reason. Yeah, it's a slightly different thing that they're pointing to. So hopefully by July, we'll have a more concrete announcement from this team, maybe others. And so that's sort of like use case one for formalization. Is the proof actually true? We don't doubt that Fermat's last theorem is true. We hope to learn all kinds of other things from the act of formalization. In this case, we actually want to know, is there a theorem here or not? Because for too many years now, we've had a situation where it's true in Tokyo and elsewhere there are doubts, right? This is not a good way for mathematics to function, right? So, right, that was latest in a long string of verification projects for different reasons. Schulze's liquid tensor experiment, which we also heard about, Schulze thought he proved the theorem correctly, but he went around the world, people were using the things that he built on top of this one extremely complicated theorem, and he said, I've gotten things past people before. He said he had IMO solutions that were accepted, he got full credit for, that he later went through and there was a gap in the argument. Okay, he said, people trust me too much. I don't want human beings, I can't get teams of human beings to check this proof. Maybe I can get teams of formalizers to check this proof. And indeed, he posed this to the entire formalization community. Could have been done in Isabel and Koch and Hollite and all kinds of other things. For whatever reason, the lean community jumped in and said, we take this challenge, we'll take it on. They worked with him for many months and eventually formalized the particular question that he had, and maybe a year after that, formalized the entire condensed mathematics that sorry? Schulze? Schulze had a proof. It was written down. Sorry. There was a gap in an IMO solution that wasn't caught at the time of that they were grading it. They gave him full credit for a solution that seemed right, and then he himself later discovered wasn't right. In this case, there's no gap. It's just that it was an extremely complicated argument, and he really wasn't sure if he got it right. And he wanted someone to check, and no one was willing to do it in natural language. He thought groups, he's a famous guy. He puts out this thing. He says it's the most important work of his life. This is already after his Fields Medal. And he still can't get people. It's so complicated. People aren't going to sit down and take their time to work this thing out that exists in his brain. And it's written down, but it's really, really hard. And the lean community jumped in and said, we'll do it. And working with him, because he doesn't know any lean, he doesn't need to know any lean. He just tells them, here's what's supposed to happen. They get as far as they can with what he's written. And then they get a little bit further every day and say, sorry, I don't understand what it says here, and so on. But through that project, by the way, there was at some point he was using the Breen-Deligne resolution that they realized this was something that was going to be a massive other project that they were just going to axiomatize. At least that was the initial idea, was to axiomatize this away and just say these are the theorems that would be proved in this big theory that we're not going to develop. And then they realized they could bypass that big theory. So through the act of formalization, not only did they certify the correctness of his proof, there was a small amount of doubt, nowhere near as much as Mochizuki. I don't think it was really doubt. He just wanted, certification. But as often happens when you go over an argument a second, a third, a 10th time, you find a simpler way to express it. And indeed, they were able to discover the simplification, and now the proof is significantly easier.
So when you say they, so this wasn't auto-formalization?
This was before AI was good at any of this stuff. This was led by Johan Komlin, Adam Topaz, and others in the MathLib community.
So, but in principle, he got what he wanted. He got some people to actually read the proof.
He got exactly what he wanted. He got people to read the proof. They simplified it. They certified it. Yeah, every last detail down to, 2 divides prime implies, like every single T was crossed. And
I guess since it's already been done, you can't really ask this question, but is this the level of thing that could be auto-formalized?
Today, that's a very good question. So it could be what I would call quasi-auto-formalized, which is all I'm interested in. I'm not a machine learning researcher. I don't need to design systems that are going to be automated. I'm a mathematician. I just want these things proved. And I want to be able to interrogate the proof, understand what's going on, understand the right level of organization, and so on. So it's possible that the AI would have the same experience as the human beings. In other words, it would read his proof, it would formalize as far as it could, and then just say, I really don't understand what it says here. Can you help me out? What's the next step? So that's the quasi, that it's not purely machine, but it's machine interacting with a human being that's doing the formalization, which is what was happening here, except it was human beings who don't know the proof trying to read the proof and translate it to a formal language. And whenever they get stuck, they ask him for help. He helps them out. They keep going.
And people are checking that the machine translation of the thing that you want to prove is actually the thing that people agree you want to prove.
Well, that's
I
the...
can imagine that there's some machinery needed to even set up the statements.
Absolutely, and that's the essential thing that we can also argue about this, but I would say no machine will ever do is at some point a human being has to say, just like when you saw the natural language statement and the formal statement side by side, you have to certify that the formal statement says what you think it says and that the definitions are what you think they are. And that's a non-trivial thing.
Who does that now?
Human beings. Human beings look at the definition and say, yes, I think this is proving what I claim it is. There are all kinds of ways to hide and obfuscate what's going on, and AI is very good at finding all of those ways and trying to. It's very lazy when you play with AI. It wants to do the lowest effort work, right? Kevin Buzzard has a great line. AI is trying to convince you that the argument sounds plausible. A human being actually believes that it's true, even if they make a mistake, that they are at least good faith human beings are trying to show you something that they believe to be true, whereas AI wants to show you what it thinks is plausible. So it's a very, very big difference. Okay, so that was one example. So as we heard, so Terry Tao and I had this project. It's just called the PNT Plus project. We knew we would get the prime number theorem we proved in, 6 weeks or something from when we started, but we knew the project is just growing in all kinds of other directions. It's a very good framework for getting a bunch of analysis and analytic number theory formalized. So, and the prime number theorem itself had already been done decades before in other proof assistants in Isabelle and Koch and so on. Our particular formalization, I was really, we developed what, I probably have to write like a complex analysis textbook or something now, because we developed this way of doing complex analysis for this purpose, but it's actually, I think, an easier way to do complex analysis in general in natural language, having nothing to do with formalization, where you use rectangles instead of keyhole contours and such as the foundational object. And it really, this is the kind of thing that happens all the time. Formalization compels new abstractions, new structures to the surface that you wouldn't have reason to think about otherwise. So I think we have learned something, I don't know if I would call it new about complex analysis, a new way of doing complex analysis that's actually much easier, even in natural language, but it's so easy in natural language that we could easily do it formally as well. And there's another vignette from Tao's formalization of this polynomial of Freiman-Ruger theorem, which is at some point, in these theorems you have some exponent, and in this case the exponent was 12. And they said, I think we can actually prove this bound with an exponent of 11 instead. Let's just see what happens when we replace 12 by 11 in the theorem. And a whole bunch of lines are still perfectly fine, and then at this line there's this red squiggle. Now Lean doesn't understand the proof. So this is the kind of thing where, in mathematics this might be a PhD thesis. Oh, can you lower 12 to 11? Someone has to read a very complicated proof, follow through. Okay, maybe that's not quite a PhD thesis. But something like, can you do this over number fields? Someone proves a theorem over Q, can you do it over number fields? You have a ring, do you really need rings, or is it okay to do it in semi-rings? And you have to sit there and follow through. It's like clerical work. It's not really deep mathematical thought. This can be automated. If you have a formal proof, you just delete the word ring in your assumption and put semi-ring and see if the proof goes through. And if not, where does it break and where might you need to supply extra arguments? So extremely efficient in that way.
Push back on the clerical.
Please.
The notion of asking your PhD student as their first project to improve 12 to 11. Yeah, they need to read through and really understand the proof, and they've learned something.
It's a great learning experience. I agree completely. We have to be very careful what we automate away. Right? There's a huge fight in mathematics education that's been going on for 70 years. A calculator can do your times table. Do you really need to memorize your times table? And there are lots of people who say no. And for my children, I say yes. I don't care that a calculator can do it. You still need to be able to do it yourself. Once you're at the point where you have automated it, go ahead and use a calculator. But we don't have that matrix hookup that, you close your eyes for 5 minutes and I know Kung Fu, right? You wake up and Like, we're doing this because we believe that there are certain skills that we need our brains to develop, and we don't have a better way of doing it other than hours and hours of difficult struggle with something. So we need to be very careful about what we allow to be automated away. On the other hand, I always use the example of someone wants to get stronger, so they go to the weight room and they put 200 pounds on the bench press, and then they take their forklift, they drive it over and lift it 10 times, right? So there's a time to use a forklift. If you're building some massive building, you use tools, and if your goal is to get stronger, then don't use the tools. That's defeating the purpose. So in exactly the same way, we have to be careful about what it is that we're trying to accomplish. If I'm trying to prove a new theorem that I'm interested in, I'm going to use every tool at my disposal. If it speeds up my workflow, I'll talk to GPT, I'll talk to Claude, see if they give me some ideas about what to do next, if they can help me with the formalization so I don't have to worry about those lemmas, and so on. I'm going to use every tool to get to an understanding of the truth. And if I'm a graduate student, and I know that I'm supposed to do this homework, and I know that the homework is supposed to teach me how to think about these problems, it's supposed to give me practice with struggling with staring at a blank piece of paper for an hour and not getting distracted, and I put it into GPT and it gives me the answer in 5 seconds. The answer is right. I should understand that I'm ruining my own attempt at an education by doing that. So yeah, these are very important, subtle things that we should absolutely be discussing. So again, formalization makes all kinds of theorem manipulation possible in real time. And this is just, scratching the surface of the kinds of things, like, we didn't know what would happen when we digitized music. And now you can carry around, it used to be an iPod with 100 hours of music. You can mix things, you can understand things in all kinds of ways. The same thing, I think, will happen when more mathematics is formalized. Right, and I think I'm going to say as little as possible about AI because maybe that's not the focus today, but I can't help but bring it in because it's making all of these advancements possible. Okay, so, right, a formal proof is not something that you read, it's something that you interact with. You've seen maybe these blueprints where you can see these theorems are already proved, they depend on things that haven't been proved, this is something that still needs to be stated formally, we only have a natural language statement of it. We're about to announce a prize for the paper of the future at the Association of Mathematical Research. We want to understand, so for thousands of years, we've had sort of two ways that you do mathematics. You do it at a blackboard. Well, actually, blackboards are only 200 years old. But you do it orally. You discuss things with people. You write it down on paper. But then the way you communicate it eventually is on papyrus or in a journal or in a PDF. And we're at the state where we need new ways. If mathematics isn't linear, but when we write it, it always is. And so we have now the capacity to develop all kinds of new ways to communicate mathematics to one another, such as things like this blueprint and all kinds of other potential systems. So we're going to learn a lot about how to communicate these things to one another, I think, in the near future. Technology is making it possible that a mere mortal like me can just step in and start doing this. So, yeah. So then let's start thinking about what the potential bottleneck would be if large-scale formalization does become possible, as it seems like it might. I would say that the next bottleneck is organization. And so what I mean by that is the reason we're able to do these auto-formalization projects, large-scale auto-formalization projects, is because they're already built on top of MathLib. So the library exists, that's the foundation for these things. And when you try to do a formalization project in a field where the library is not so strong, it will struggle. And so, but the library contains the canonical version of everything. The most abstract, the most general, the most reusable. In order to have a coherent, interconnected library, it has to not be duplicating arguments. It has to have the right tactics, but also the right theorems in the right locations at the right level of abstraction. And so we've already made great strides in AI helping us with formalization. And I think the next frontier is it needs to help us with canonization. So auto-canonization, can you take a 500,000 line lean proof? Okay, we got from 500,000 down to 200,000, but that's still not It's not teaching us what's the essence of the proof. What are the right objects through which we express what's actually there? And it's more than refactoring. Refactoring doesn't always refactoring is like, here's the proof. How do I golf it? How do I shorten it? How do I make it slightly slicker? Canonization is, what is the right way to state this theorem? What's the right underlying object? So for example, I didn't say it here, but in MathLib, there's a notion that exists nowhere outside of MathLib called group with zero. We have ring, we have semi-ring, we have monoid, we have all kinds of things. We have, and in MathLib, they realize that there's a core concept that undergirds all kinds of other mathematics that's a group with zero. And a group with zero should be a foundational concept, and it will be in textbooks that'll be written over the next 5 to 10 years. But it's something that isn't anywhere in the literature, but it is an absolutely key bit of mathematical abstraction. Every bit as valid as a field or a ring. Okay, you've never heard of group with zero. So that's one instance of canonization that you only discover through this kind of work. So what would be, if we got AI to help us with canonization, that would, and again, if it's doing things automatically, we want to understand. So the fact that it can do it automatically doesn't mean we should just let it, send it loose and not care what it's doing. We need to also have it feed back. So when you're doing research mathematics, you want that research formalized. You want that formalization, just the fact that you formalize it, that's not the end of the story. You want to canonize it to grow the library, and that'll help you do research, and we get this positive feedback loop. So again, the acts of formalization and canonization might seem new, but they're really, I would like to claim, continuations of standard things that we do in pure math research. When I was younger, I hated writing papers. You prove a theorem, you know it in your head, you can explain it to anybody on a blackboard, you can explain every detail, but now you have to stop what you're doing, not do new research for months at a time to write this thing down on paper. That's the way you get credit. We decided that you can't just go around giving lectures about things. Your lectures, you can post your lectures on your CV, but that's not what gets you a job. You have to start writing papers. Okay? Papers published in journals is how we decide that's what counts. Well, going from the blackboard to the paper version of something, we realize has tremendous amount of value, right? I was wrong in my youth to hate, I don't know. I still hate writing papers, but I know that they're essential. I know that I'm going to learn so much about the proof that I thought I understood inside and out when I actually write it down. When I write down every last detail, check that everything is right. Should I be referencing, this idea actually comes from somewhere else? So writing up a paper from knowing how to prove it on the blackboard reveals so much, and it reveals just how much more research there is to be done. The act of writing a paper is part of the core skill set of a research mathematician. And so, yeah.
So, but in principle, you could imagine that you just give a recording of your lecture or your blackboard.
Absolutely.
And it does away with this.
Absolutely.
But maybe it doesn't give you the best notation or the right definitions, or it just gives you something.
That's right.
So, how does this help then?
Well, I'm trying to. So, the shortest answer is that AI doesn't need you for this part either. So I don't see any reason, at least I haven't, every time I tried to articulate a reason that AI can't do any one of these steps, I have failed to find one. Okay? So AI could come up with a theorem. It could talk about it with itself, the agentic framework where it just keeps talking until it is sort of having an internal dialogue. It comes up with what it thinks is a proof of a theorem. It writes that theorem up in PDF. Then it automatically translates that theorem to a formalized version. And then it goes over what it's formalized and says what's actually the right level of abstraction and canonizes the whole thing.
So it certainly can come up with theorems. The question is, are they interesting theorems?
And human beings, right. And I believe that human beings will still be the ones who determine what we think is interesting or not.
Yeah, but we probably don't want to have the computer produce all possible theorems.
Right. So we want to separate what
Sort through it.
exactly. We want to separate what we want from what it can, at least in principle, do. And over here, I don't see why it can't do all of these eventually, at least at the scale that and at the pace at which the tools have been advancing. I don't see why it can't do each of these things. What I'm trying to say is, forget about AI. What do I, as a human being, want to do? I want to prove theorems. I want to understand new things. I realize that I also have to write those things up, or else it doesn't count. I think in the future, we will also want people to then formalize it. That's when you really understand that paper. And maybe the final level of understanding, the kind of, the Grothendieck limit is now you canonize everything so that it's really in the most abstract, the most reusable sense.
And are you imagining the formalized and canonized are automated, or is this something that a person does for their own?
So I think that a person does it for their own understanding, but AI can help. AI can help with every single step of this process. If I'm thinking about a theorem, I can talk to GPT and it'll bounce some ideas off of it. If I'm writing a paper, these days I tell the AI, here's what I want to say, here's a list of things, write me the outline, there's the outline, no, I don't like it, let's iterate until I'm happy with what the outline says, and now let's iterate until, get this paragraph right, okay, great, I'm happy with that paragraph, get the next paragraph right, and so on. So it's drastically speeding up my workflow at writing papers. It's drastically speeding up my workflow at formalization. What's the name of this theorem? I'm going to go into MATLAB docs and try to find which of these 1,000 theorems is the one that I want to use in this instance. No, go look. LLMs are amazing at lookup. What's the right theorem for this? I didn't put it here, but actually John Morgan and I had a project that we started at the Simons Foundation. There was a workshop on lean and formalization last June. And we started a project, the way that in MATLAB, the way that the fundamental theorem of algebra is proved is through complex analysis, Liouville's theorem, standard argument. John says, no, come on, that's not how it should be done. It's something about continuity. Don't use analysis to prove a theorem. In continuity, it should be about winding numbers and walking the dog argument. I said, okay, great, write it up. So he wrote up a blueprint of it, and we spent up until about a month ago, we were doing this very leisurely for fun, about like an hour a month. We would hop on a Zoom call, and I'd be looking up the theorems in the library and adding them one by one to our blueprint. And then, and I'm constantly asking Claude or GPT, oh wait, there should be a theorem that says this, find it for me in the library. It helps me with that. You want to do a proof through Brownian motion? Let's write up a blueprint. Yeah. So let's. Yeah. 1D Brownian motion just entered the library, so we should be able to. It has. It's now in the library. One-dimensional Brownian motion.
Now meaning what? Oh, no, you need
Now, as of I think 2 weeks ago.
You need two-dimensional.
They're working on 2D. They're working on arbitrary dimension, but one-dimensional Brownian motion I think was just added to the library. So we could have another project, okay? But the point I wanted to make about the project with John is that we got about a third of the way through our blueprint, just iterating in this way. And then Codex came out, and I turned on the Codex helper in VS Code. And I said, okay, here's the next theorem. Just read to me where the first sorry is, or the first natural language statement that doesn't have a corresponding formal statement. Can you state it formally for me? It thinks for 5 minutes, it comes back with a statement. I look at the statement, I say, that looks pretty good to me. Can you give me a formal proof? The natural language proof is there. Of course, the natural language proof is in 1,000 textbooks. It could have come up with it on its own. In this case, John wrote it. We wait 5 minutes, it comes up with a formal proof, and Lean accepts it. It actually iterates with Lean a few times. It writes a proof, it runs lake build, it didn't build right, there's an error message, okay, let me try fixing this line, and it iterates like that, and then gives me the formal proof. And we spent the hour just querying GPT, and we got from about 30% done to about 60% done. And then I was taking a train down to DC. I get on the train, I turn on Wi-Fi, and I said, why don't you just try to finish the rest of the argument and get as far as you can, and when you get stuck, ping me. And I started doing other things. I forgot all about it. An hour later, I look back. It had spent 45 minutes, and it finished the project. And it was done. Okay?
The benefit of working with John Morgan was lost in the end because GPT did the rest, or
I think that we learned what we wanted to learn from this experiment. By the way, the next thing I asked it to do is, okay, now we have a formal proof. Go back over this argument and actually extract the things that we should be adding to MathLib, the things that aren't in MathLib. And we had proved that the exponential map was a covering map. And I started adding that, and it said, wait a second, that had been added to the library while we were working on this project. I think in January it got added to the library. It wasn't there when we started in June. So, yeah, so it can help with each of these things. And my goal is always to learn. What can I learn from this step? What can I learn from that step? And I think each of these steps gives you a new insight, deeper insight, ever deeper insight into what the mathematics is trying to say. There are a lot of questions. Should we take some more questions? Or I'm almost done, actually. I wanted to leave plenty of time for questions. Can I just finish and then we come back for questions? So, right. So the first arrow is already recognized as a necessary component of research mathematics. Nobody argues that you can stop at giving talks. You have to write up the papers. And the second arrow is just because it's written up doesn't mean it's written sufficiently carefully that it can be explained to a computer, either by humans or with AI assistance. The third arrow is just because it's formalized, just because you've written 500,000 lines of code, doesn't mean that you have extracted the generalization, the abstraction, and gotten to really the heart of the matter at every step. These are all time-consuming endeavors that require real skill, but maybe we'll eventually come to appreciate them just as much as we now appreciate epsilon delta calculus and abstract rings. It might take a generation or two. I actually think it's going to come a lot faster, maybe much faster, again, thanks to AI, and then mathematicians might become as accustomed to working formally as they are with Lean. So let me stop there. Thanks.
On the project that you did with John Morgan, did you only use ChatGPT or did you use a bunch of Claude agents? And then I guess the quote, the book that was formalized last week by the student of Tim Gowers, whose name I won't try to pronounce.
The Facebook group, yeah.
They said that their compute budget was around $100,000. I was wondering what your compute budget was for this little project, and if you had any guidance on how to estimate how much compute you need in order to do formalizations. I'm sorry if you went over this.
Not at all. So let me just show you what the project looks like. It's one of these blueprint projects. So here's a dependency graph. And everything's green. That means that all the theorems have been proved already. The last theorem is, let's see, can you see that, or should I zoom in a little bit more? So the last theorem is you have a polynomial over the complex numbers of degree greater than 0, then it has a root. And the theorem just above may be something like eventually winding number. So this says if you have a polynomial with positive degree, then, okay, you have to understand what filters are. This is another one of those things that in formalization you realize that there's a better way to do calculus, which is the filter language. So filter at top means for all r sufficiently large, there exists a function from the circle into the complexes so that the function is equal to the polynomial and has the same winding number. So unpack and the winding unpack this again. It's well, you can read that. Actually, you can read the natural language. You can read the natural language on top and then see how it's translated to the formal language. The compute budget, I can tell you, I used to spend $20 a month on Claude, and that's what we did to get to the 30% of the blueprint done. And then and GPT was bad at coding and it was bad at Lean. And Codex, which is the agentic GPT, Codex combined with GPT 5.4, once I saw that working, and that's what finished this project, I said, okay, it's worth my $200. So my budget is $200 a month that the NSF pays. So $200 a month, what is that? $10, a little under $10 a day. It's a coffee.
Everyone has been trying to convince me that stochastic analysis needs this kind of formalization, in particular my book with Sri.
That would be amazing.
Why? Why?
Oh, why does it need it?
Yeah.
It doesn't need it.
It doesn't need it.
No.
But why would it be amazing?
So I tried to argue all of the benefits of digitizing mathematics. I think there are quite a lot of benefits. I think the act of doing the digitization, we inevitably, I can't predict why we'll learn something. But in every project,
We may learn.
we may learn. Yeah, in every project that's been formalized, the act of formalization forces people to think about things in ways that they didn't have to in natural language, and you end up learning a richer, deeper way of doing what you're doing. It could be very interesting. I don't know who's the chair.
I have a question about communication and organization, I guess. So when you make a blueprint like this, it looks pretty good. I started using Lean a couple of years ago and was very bad at it, but have gotten like 10 times more productive without getting any smarter because like the tools are better. But still, with the blueprints, mine looks terrible because I've made so many like little lemmas and theorems that probably were not very hard to prove. But like that's kind of how Lean encourages people to do things. But it clutters up the blueprint so much with not very difficult or important things. I didn't try to prove the prime number theorem, but I have this phenomenon that the blueprint is not actually helping me understand or communicate.
Yeah. So the reason this looks like this is that there's 10 different projects now being run in the PNT Plus repository. So the prime number theorem, I think, is that little chunk. That's all done, and then we have 1,000 other things that are works in progress. The key idea there is don't blueprint every little lemma. You don't need necessarily need a node in the graph for every bit of API. So just the important things, and then you can have something that's visible. This is no longer useful.
Yeah.
Right? This isn't how we're coordinating things anymore. It was very useful when we were doing, that chunk, and now the project has exploded. Maybe we should separate it out into, like I said, there's 10 different projects, and you can even see the 10 different chapters in the project. Let's see. Yeah, so the first 3 approaches were the weak, medium, and strong prime number theorem, and then there's, all this other stuff on top of it. We've set it up in a really nice way, and that's why we don't want to break it off into their own projects. But yeah, pretty soon we might have to, because the dependency graph really is useful to be able to look at, and that's not a dependency graph you can look at as a human. But we have other ways of coordinating things over Zulip and so on. So, yeah, so the short answer is don't put everything into the blueprint.
Henry mentioned before that there's also a physics library besides a math library, and I was wondering if there are any differences in formalization between the two fields.
Yeah, maybe I'm going to say something controversial. The physics that can be formalized is by definition mathematics. The distinction between mathematics and physics is our epistemology, right? We sort of, at some point we were in the same department, and then we said, no, you need absolute rigorous proof. And they said, I don't have time for that. I'm trying to get somewhere. I'm going to do this calculation. I'll get an answer. I don't know why. I don't know how to integrate over Feynman diagrams, over the space of all Feynman diagrams. But I know how to do a calculation. I don't know what the axiomatic, by the way, Newton broke the axiomatic method, right? We did not have a theory, an axiomatic theory for fluxions. And for Newton's time and Leibniz's time and the Bernoullis and Euler, calculus was just fine. It wasn't until we got to Cauchy and Fourier. Cauchy proved that limits of continuous functions are continuous. And Fourier proved you could add up sines and cosines and get a sawtooth. Okay, so now we have a crisis. Now we have to solve it. Epsilon delta is what resolves that crisis. So physics has its own epistemology. That's why they broke off as a department. To the extent that they can axiomatize what they're doing. And by the way, Michael Douglas just had a project where he axiomatized. Does anybody remember what it was? A big chunk of a physical theory. When you axiomatize physical theories, you're doing mathematics. For me, the definition of mathematics is something that's, building a logical system from an axiomatic framework.
Thanks.
So.
Thanks. I'd be interested to hear about the budget for that formalization of the 500-page textbook. I have a 2,000 pages of advanced mathematics that, if they were could be formalized, could actually help me. Although I wouldn't want to have anything to do with it. But I think there's an overdue. Or it sounds like it's overdue for a serious discussion of resources, because whatever is going into this approach to mathematics is being taken away from other resources, and this is clear from I haven't been able to get a straight answer on how much of the funding for this new institute at Carnegie Mellon has been taken away from the NSF budget. I think it's about 10%.
Sorry, do you say you're saying the fact that ICARM exists is taking 10% away from the NSF, or the fact that, or was ICARM's budget cut by 10%? I don't understand.
No, ICARM. If the NSF budget for mathematics has been kept flat for the past year, next year again, once again, the proposal is to cut NSF funding in half. But at the same time, money is being diverted to ICARM. Well, this is happening somehow on the basis of discussions among the people directly involved, but the whole mathematical community is affected by this. And as far as I know, there has been no serious discussion of whether mathematics really wants the resources to go in this direction rather than to more traditional approaches to mathematics.
Yeah, so let's separate two things. One is about government, the NSF, the decisions that they make to allocate tax dollars. Why the NSF chose to add ICARM as an institute as opposed to, which one was just shut down? The one in Wisconsin, right? They had an NSF institute that 5 years ago was not renewed. Minnesota, thank you. The Minnesota one was not renewed. So, IMA, thank you, yeah. So, the NSF operates NSF institutes, ICARM, ICERM, the one at UCLA, Rutgers. The DIMAX used to be an NSF institute. It's now a DARPA institute. So how they choose to allocate their budgets is up to them and the problems they're trying to solve. Maybe you don't like that they allocated it to a center that's devoted to formalized mathematics.
It's not a question of what I do or do not like. In what sense is that decision a reflection of the general preferences of mathematicians? And of course, there's nothing that obliges the government to take the preferences of mathematicians into account. Nevertheless, one supposes that as mathematicians, this is expression of our interests.
Yeah.
You could argue that going to the moon took money away from math, but later got a lot of money back into math.
Well, this is the budget of the Directorate of Mathematical Sciences, so it's specifically
right. But that directorate goes and has a panel where they invite a whole bunch of mathematicians. I wasn't on that panel. I can't tell you what the discussions were. I don't know who else applied to be an NSF institute and was denied. So, those are decisions that are made by. I would say actually that is the fact that they run panels with mathematicians who are not. It's not like they have Kevin Buzzard and Leo Demora on the panel, and they get to decide what the next NSF institute is going to be. So I would say as much as. Insofar as imperfect a system as it is for gauging mathematical interest, I would say where the NSF puts their money is as good a reflection of what the mathematics community wants. May not be what you want, may not be what I want, but we have, the UCLA one, ICERM, IPAM, and now ICARM. So
That was one point.
That was one point. Okay, so let's separate what how decisions are made collectively from what profit-seeking corporations like Math Inc. and Axiom and Amazon and so on are doing in mathematics. You might say they should get out of mathematics. They shouldn't be involved in this subject at all. I actually think in 5 years they will be out of mathematics because they're only using mathematics right now to prove who's the best among them. Math is a really, really easy playground, and the only reason they're involved is because that's a playground where they get to attract, by doing some publicity stunt, they get to attract VC funding. Okay, and then they'll get bored of us and they'll move on, and we'll be back to just doing math for our own sake. In the process, though, they might develop all kinds of amazing tools that help us learn new mathematics. And so that's my viewpoint in working with them. You asked about what the budget of Gauss is. They tell you nothing about what their budget is. I don't know what their evaluation is. I think there's nothing, at least that I know, that's public about them. Axiom, well, you can maybe ask Ken Ono what the story is there. They did announce that their seed, their Series A or something, just went through, and their valuation, I don't know how much they raised a couple $100 million. Their valuation is over $1 billion. So
I calculated that about what not just Axiom, or it's an estimate, a very rough estimate, that the what's it called, the market valuation would pay for the 200 graduate student slots that have been lost this year, approximately for the next several thousand years.
So here's the, I think, mistake is to think that money would have gone to graduate students had it not gone to Axiom, right? This is, that money would have been somewhere completely different in the ecosystem, and now it's doing something in the direction of mathematics. So there's a variety of ways to interpret what's going on.
All right. So maybe we should end on that optimistic note. Let's thank both Alex and Henry again.